Okay, picture this. You're building a machine learning model to predict house prices, and you feed it the local US zip code, say 2004. Makes total sense, right? But wait, what if your model takes that zip code, compares it to a house in zip code 10,002, and mathematically concludes that the first location is exactly twice as large a signal as the second? By treating a zip code like a regular continuous number, you've actually just taught your model complete mathematical nonsense. Welcome to today's Explainer. We're diving straight into exactly how machine learning models process the messy, non-numerical, perfectly human real world. We'll explore the incredibly cool process of taking categories, things like colors, animal species, or street names, and translating them into a language that a mathematical model can actually understand. And more importantly, how to do it without totally breaking its logic. So here is our roadmap for today. Number 1, what is categorical data? Number 2, translating words into numbers. Number 3, the pitfalls of labeling. And finally, number 4, mastering feature crosses. Let's jump right in. All right, section 1, what is categorical data? Let's start by busting a few myths about what machine learning models actually inherently know. The absolute fundamental difference we need to establish here is between true numerical data and categorical data. See, true numerical data can be meaningfully multiplied. For instance, a house that's 200 square meters is, for all practical purposes, exactly twice as large as a house that's 100 square meters. Categorical data, on the other hand, draws from a very specific set of possible values. We're talking about things like animal species in a national park, street names, or house colors. You literally cannot mathematically multiply a maple tree by a dog. It just doesn't work. So, the absolutely crucial takeaway here is that models only do math. If we just randomly assign index numbers to our categories, say we give orange the number 1 and purple the number 6, and then feed them in as continuous numbers, the model makes a fatal mathematical assumption. It's going to assume purple is 6 times greater, or maybe 6 times more likely than orange. We desperately need a better way to translate this data.
Which brings us to section 2, translating words into numbers.
So how exactly do we take a discrete word, like red, and turn it into a number the machine can safely digest? Well, we use a vocabulary encoding pipeline. First, we start with the raw string itself, like red. Second, we assign it a unique index number so the computer has a way to reference it, but we definitely don't stop there. The real magic happens in step 3, where we convert that index number into what's known as a one-hot vector. In a one-hot encoding, you get this really elegant diagonal line of ones across your data. Each category is represented by an array. Exactly one element in that entire array is set to 1.0, representing the active category, while every single other element is strictly 0.0. This completely prevents the model from assuming any sort of mathematical hierarchy between the colors. Oh, and to save memory, engineers use this brilliant little sparse representation trick. They just store the position of the 1 rather than storing thousands and thousands of zeros. Pretty smart, right? Now that works wonderfully for a handful of car colors, but I want you to take a second and think about the scale of real-world data. What if your categorical feature isn't just 3 or 4 colors, but literally every single word in the English language? Think about the sheer scale of these high-dimensional features. We are talking about roughly 500,000 words in English, or 42,000 US postal codes, or how about 850,000 unique last names in Germany? If you tried to build a one-hot vector for a German last name, you would have an array of 850,000 elements with exactly one single 1 and 849,999 zeros. That breaks down so fast because the computational training costs are just immense. So for data this massive, ML experts bypass one-hot encoding entirely. Instead, they rely on dimensionality reduction techniques, things like embeddings or the hashing trick, to make it manageable. Moving right along to section 3, the pitfalls of labeling. So we know how to mechanically translate the data. But what happens when the starting data itself is inherently flawed? In machine learning, data that's manually labeled by humans is called gold labels. And they're highly desirable because, let's face it, humans usually capture real-world nuance much better than a machine can. But gold does not mean flawless, not even close. You have to watch out for vulnerabilities like human error, unconscious assumptions, malicious intent, or even just simple disagreement between people. These datasets require intense, rigorous scrubbing before they ever get anywhere near a model. Actually, any two human beings might label the exact same data point entirely differently. I mean, is that an orange shirt or a red shirt? Is that specific email actually spam or just an annoying newsletter? This variance is measured by something called inter-rater agreement, usually using statistical tools like Cohen's kappa. And it proves that even our absolute gold standard labels possess a pretty deep degree of subjective variance. To get around the slow, tedious speed of human raters, we sometimes use what are called silver labels. These are categories automatically determined by other machine models. But here's the catch. Machines notoriously lack common sense. If a computer vision model generates silver labels by mislabeling a photo of a chihuahua as a blueberry muffin, which, yes, happens, the downstream model trained on that data is going to inherit that exact same absurdity. Or imagine a sentiment analyzer assigning negative weights to completely neutral words. Without human oversight, these flaws don't just sit there, they compound. And that leads us to Section 4, Mastering Feature Crosses. Assuming our labels are perfectly clean and efficiently encoded, we are now ready to unleash a literal superpower that helps simple, linear models solve highly complex, nonlinear problems. It's called the feature cross. This involves taking the Cartesian product, which is essentially mathematically multiplying, two or more categorical features to capture exactly how they interact. You can kind of think of it as the categorical equivalent of a polynomial transform for numerical data. It allows our models to learn that a very specific combination of traits means something entirely unique, totally separate from the individual traits standing alone. Let me explain what that actually looks like in practice. Imagine we're classifying a dataset of tree leaves. We have one feature for the edge of the leaf, say smooth, and another for the leaf's arrangement, say opposite. By multiplying these categorical one-hot vectors together, we synthesize a brand new feature, smooth_opposite. Now, if a leaf has both of those traits, this new feature gets a value of 1. Our model can now heavily weight this specific combination to perfectly identify a particular tree species. It's absolutely a game changer. And this is exactly why feature crosses are so absolutely vital. In the TensorFlow playground, for example, if you try to classify healthy versus sick trees that are arranged in a complex spherical pattern, simple straight-line features fail completely. They just can't do it. But by crossing features, essentially allowing the model to look at x1 and x2 simultaneously, the neural network can suddenly draw perfect circular boundaries, cleanly and beautifully separating the sick trees from the healthy ones. But a quick warning, with great power comes, well, massive computational cost. If you cross a sparse feature that has 100 elements with another sparse feature that has 200 elements, you don't just get 300 elements. You get their product, a massive 20,000 element feature. This exponential explosion of empty data is exactly why ML practitioners have to rely on deep domain expertise or automated neural networks to discover only the most useful combinations. You definitely don't want to just cross everything blindly. So, we've seen how messy human words are transformed into rigid ones and zeros. We've seen how surprisingly subjective our gold labels really are, and how combining features can unlock just incredible predictive power. But remember, it all starts with the categories that we define. So I'm going to leave you with this somewhat provocative thought to ponder. As our machine learning models constantly ingest the real world, how much of our own unexamined human subjectivity is being permanently encoded into these categorical matrices? Thanks so much for joining me on this explainer, and keep learning.